Okay, boys, just to finish the normal distribution, we're going to look at using the normal distribution to analyse real-life situations. Okay, so let's look at our first example. The company produces 1 kilogram packets of sugar. A quality control check found that the weight of the packets was normally distributed with a mean weight of 0.995 and a standard deviation of 0.03. The company policy is to reject any packet with a weight outside 2 standard deviations from the mean. What is the smallest weight allowed by the company? Okay, so you don't need a diagram for this, but I'm going to draw one anyway because it's always good to have a picture of what's happening. Okay, so let's just click on the pen tool. All right, so here's a little sketch of the normal distribution. I'll do. And in the middle, we have the mean, which is 0.995. And then we have 1 standard deviation above and below the mean. So I'll put down, that'll be 1.025. Right, because I'm just adding 0.03 and 0.995 together to get the 1 standard deviation above the mean. And now, obviously not to scale, but the next one will be 1.055. Now below the mean, I'm going to subtract 0.03, that's 0.965. And then subtract 0.03 again, you're going to get 0.935. So 0.935. Okay, so let's keep that picture in mind. Right, again, it's not necessary to draw this in, but that is your average. Now, anything outside 2 standard deviations, so anything in above that or to the left of that will be thrown out. So the smallest weight will obviously be this one. This is our average, U, and this is our average subtracted 2 standard deviations. So the smallest weight allowed by the company will be 0.935 grams, because anything smaller than that will be thrown out. Now, what is the largest weight? Well, now we've got our picture here. The largest weight which is allowed is 1.055 grams. Now, without the picture, you could have just done this, 0.995 plus 2 times the standard deviation. Okay, and that'll give you that number there. Okay, so no picture needed, but for the sake of the examples, it's good to see what we're doing. Okay, now what percentage of packets will be rejected? Now, the rejected part is going to be anything outside of 2 standard deviations. Now, we know that within 2 standard deviations, let's just put that in, that 95% of the data lies within 2 standard deviations. So that means the products you're going to throw out will be 5%. So I'm just going to write down 5%. 100% minus 5%. So 5% are rejected. Now, what percentage of larger packets will be rejected? Now, we're talking about larger packets. That means we're really talking about this region in here. Okay. So what percentage of larger packets will be rejected? Well, let's think about this. We have 2 regions that we're essentially rejecting. So this 5% consists of that section there and this section here, which means because it's symmetrical, this bit must be 2.5% and this bit over here must be 2.5%. Okay, so if we're talking about the larger packets, we're talking about 2.5%, right? So in other words, we're looking at the working out, it's going to be 5% divided by 2, 5% divided by 2 equals 2.5%. Okay, so that's done there. Let's move on. Okay, so I've got the mean shelf life of the spice rack is 13.4 weeks, and the standard deviation is 1.8 weeks. Would a shelf life of 20 weeks be unusual? Well, again, let's just have a little diagram in our heads. You don't have to draw this, but you can picture it. Here's your standard normal distribution. Okay, so there we go. We've got it goes up there and then down there. Okay, so in the middle, you have 13.4. And then one standard deviation away from that is 15.2. 2 standard deviations from that is 17. 3 standard deviations from that is 18.8. Okay, now 1 standard deviation below it is 11.6. And then the other standard deviation below that is 9.8. And then the third standard deviation below is 8. Okay, so if you're talking about 20 weeks, 20 weeks lies beyond 3 standard deviations, doesn't it? Okay, so don't forget this is your average. So let's look at this region. We know that 99.7%, right? 99.7% lies within 3 standard deviations. So yes, it is very unlikely that the shelf life of 20 weeks would be existing. So it would be very unusual to have 20 weeks, because 20 weeks is way beyond the 18.8. So I'd say yes, the answer is yes. Since 20 weeks is more than 3 standard deviations above the mean, okay. Now the other interesting thing is you also mentioned the percentage of data which is there. So if we've got 99.7% of the data within 3 standard deviations, that means 0.3%, right? So 0.3% is this shaded region here and this shaded region here, which is symmetrical. So that means that bit there, beyond 3 standard deviations, must be 0.15%, right? So, and we could say, adding on to that, and only 0.15% of the data lies above 3 standard deviations, okay, from the mean. Okay, so let's have a look at the next question. So yeah, the answer would be very unlikely for that one. So find the Z-score for shelf life of 15.5 weeks. Well, we know our Z-score formula here, don't we? The Z-score formula is X minus mean divided by the standard deviation. So that's going to give us Z equals 15.5 minus 13.4 divided by 1.8, which equals 1.16 repeater. Okay, that's easy. Now let's have a look at our next question. It says, what percentage of shelf lives would be expected to be between 13.4 and 15.5 weeks? Well, 13.4 is the mean, isn't it? So if we just draw a little diagram again, okay, so we can see what's happening. There's your standard deviation. So your normal distribution, should I say. Now, in the middle, which is the mean, that's 13.4. And 15.5 will be somewhere over here. So this is the region that we want. Let's draw a line down the middle there. Whoops. So I want that region there. So in other words, I want to have the probability that random variable x, whoops, rub that out. Random variable x is between 13.4 and 15.5. Now, the less than or equal to is not necessary. It's not wrong if you put it because we'll be getting the same answer. We'll stick to the between though. Now, that's what we want to try and find. So, and we're going to use that using the z-score table. All right. So we're going to have to use z-scores. What I'm going to do though is first I'm going to break this up. This is equal to the probability of x less than 15.5 minus the probability x less than 13.4. Now, we want to work out the z-score, which corresponds to these numbers, so we can write down an equivalent expression involving z-scores. Now, in the previous question, they already got you to work out the z-score 15.5. Okay, so this will be the probability. Now, switching to z now, z less than 1.16 repeater. Okay, minus, now we already know what the z-score of 13.4 is because it's the mean, that will have a z-score of 0. Okay, so we're going to look at the table now and we're going to try and find a number very close to 1.16. Now, we're going to choose 1.17 as a 2 decimal approximation because we're using the Z distribution table, which goes to 2 decimal places. Okay, so that's what we're going to use. All right, so on your Z distribution table, let's see if we can find 1.17. Okay, so 1.17 will be right here. See, there's a 7, there's 1.1, so 0.8790. Okay, so that means we have 0.8790 minus, now we don't need to do too much work for this one. We don't even need to look this up in the Z table because we know that 50% of the data, lies below the mean. So we know that probability that Z is less than 0 is 0.5. Okay. Now, that should give you an answer of 0.379. Okay. So that is your answer. Now we could obviously express that as a percentage. Okay, so we could write that down as, so that would be sufficient. Or you could write it as 37.9%. Now I just want to make sure you understood the inequality part of this. So if we go back to here, you'll notice that I've written two probability expressions there, two probability terms. I've broken this up because x less than 15.5 is here, this region here, and less than 13.4 is from here to here. So if I subtract those two regions, I'm left with this region in here over. All right, so that's why I broke this up into two inequalities. All right, let's have a look at the next bit, which is 2 year 7 students. Oh, sorry, year 7 student, year 8 student. Now, in year 7, at a school, the mean weighted students is 59.4 and the standard deviation is 3.8. In year 8, the mean was 63.5 and the standard deviation was 1.7. Now, John in year 7 and Ding in year 8 both weighed 68. Which student is heavier in relation to the year? All right, let's have a look at the information they give us. Now, they tell us for year 7 that the mean is equal to 59.4 kilograms, and they tell us that the standard deviation is 3.8. Alrighty, now for year 8, they tell us that the mean is 63.5 kilos, and standard deviation is 1.7 kilos. Okay, now we've got two students. One is John. Now John is in year 7, right? Now he weighs 68 kilos. Now what I'm going to do with John is we're going to find out what Z score he has. So that's going to give me Z is equal to 68 minus 59.4 using my Z score formula, divided by standard deviation, which is 3.8. That's equal to 2.26. Now then we have Deng. Now Deng is a year 8 student and he also weighs 68 kilos. Okay, so we're going to work out the Z score for that. That is 68 minus the mean, 63.5, divided by the standard deviation, which is 1.7. That should give you 2.65. Now, if you look at Deng, he's actually more standard deviations above the mean than John. So we would say Deng is heavier. Deng is heavier compared to his year group. Right? Since his weight is more standard deviations above the mean. Okay. All right, so that concludes the worked example.